Now another CE method is called the MEKC, okay, the Micellar Electrokinetic Chromatography. As the word suggests, your MEKC uses micelle. Why do you need micelle? Okay, this process is based on partitioning. Okay, and by partitioning in analytical chemistry, it means using different solubilities in different phases. Okay, the mobile phase, in this case, oops. So micelles are made of surfactants. You know, surfactants means you have a head there that's charged, and then the tail that's normally hydrophobic. And these are found normally in soap or shampoo, right? So the surfactants help to dissolve these organic compounds because of the London dispersion forces of similar interactions. And some of these analytes dissolve better in the micelles, while other analytes dissolve better in the aqueous phase because they're more polar. So the differences in the solubilities allow the analytes to be separated. And the advantage of this method is that the organic compounds, normally that's neutral, organic compounds, can also be separated. Because when organic compound is neutral, your micelle, the tail interacts with them, then you have a charge there, right? What that's is you tag together and it becomes a one bigger molecule, but now it's charged. So now that the micelles, are formed, right? For it to be formed, we also need the surfactant concentration to be high enough. Now remember, if you have learned polymer and micelle, we call it the CMC. This concentration that's high enough is called the critical micelle concentration. If you don't have enough of this surfactant, it doesn't form the globule, right? It doesn't line up this way. Okay, so micelles are formed by different numbers of surfactant molecules, right? Aligned this way, okay, the one round, like a sun, right? Depends on the surfactant used. They are dynamic, always changing, which means they will form and break very fast. It's very dynamic, spontaneous, in, out, off, and on, so that the molecules can get in and out of the micelle. And that also means that SDS is the most commonly used surfactant, right? Because it's affordable, you can say very cheap, available in a very high purity, right? For MEKC, okay, MECC. The CMC for SDS, sodium potassium sulfate, is 8 millimolar, and the number of surfactant molecules to form the micelles is around 58 at 298 Kelvin. Okay. Now SDS, right, is a kind of an anionic surfactant because the head that's polar is negatively charged. Your tail is always neutral, there's hydrocarbon. Right? And because SDS micelle has many negatively charged groups, highly anionic, and move very slowly through the capillary because the attractions of a very positive voltage, if you recall. So the analytes will interact strongly with the micelles. We have a longer migration time. And the ones that have a lower interaction will just flow very fast. Okay, just talk about this part. Yeah. So we call the micelles in the MEKC that they refer as the pseudo-stationary phases. Okay, pseudo, like quasi-stationary, like acid. Okay, moving phases that act as the stationary phase. Good. Examples of a micelle marker, we use a Sudan tree. Okay. Good. Now MEKC applications, right, very useful, versatile. We use to separate neutral compounds. As we know, electrophoresis, you have voltaic charges, but if you're neutral, you are not affected by anything. So we need to do some tagging, interaction using a surfactant. So even though the charged species, right, will also be separated, we don't focus on the charged species because it is simpler to use the CZE, your capillary zone electrophoresis, to analyze them. Now, polar neutral molecules will dissolve well in the aqueous phase, right? They will move together with the EOF, and the analyte dissolve slightly in the micelles will also move slightly slower than the EOF. The analytes which dissolve very well in the micelles will move much more slowly. So hence the different species can be separated, right? We talk about the VX, the formula, right, take into account of the VEO, VMC, okay, of migration velocity of the micelle, right? It does support the separation of the neutral molecules. So, the conclusion is the K star, we call it the phase capacity ratio, right? If it's equal to 0, which means there's no interaction with the micelle at all, then your Vx is your VO. Now, when the K star is large, the Vx is, right, the sum of the VO and VMC because of the strong interactions with the micelle. Okay, so the order is that when you have more polar compounds, okay, then the hydrophobic compounds, right? And one of the main real advantage of the micellar electrokinetic chromatography here, the MEKC, is that by adding surfactant to create the micelle, right, the neutral compounds can be separated by applying voltage, right? You see, when we start saying that, oh, ECE, charged particles, neutral means you just, in the middle, doesn't move, but now we can make it happen. So there's a real breakthrough. Okay. Here you see this little snapshot of electrophoregram here, right? So I just put a quote, it's called the migration window. Talk about the solubilized solutes here. Now remember T0, right? The first signal that comes out is always a neutral molecule. We normally use an EOF marker, like in this case we say some example, methanol. So you can see that what comes out first, the hydrophilic solutes, right? And then T1 could be a sample, analyte 1, analyte 2, solubilized solutes here. So over on the right side will be something very hydrophobic, for instance your Sudan 3. So just take note how you use this terminology. What is a migration window? Okay, the time difference between the T0 and your TMC here. So this slide shows in a tabular form the comparison of the different kinds of surfactant you use in the MEKC, about the critical micelle concentration CMC, and the aggregation numbers AN. Okay, and we choose SDS for a very good reason. It's the right number in terms of both AN and its CMC. You can see also other surfactants as cationic, pseudoionic, and non-ionic. Here, you see an example of a small chromatogram of this MEKC, right? Now, this is from research by Professor Lee as well here. Now, the difference is, right, you want to determine this toxicant called the pyrrolizidine alkaloids in traditional like TCM kind of medication. And you can see that the 1, 2, 3, 4, right, are signals as positive, and the first EOF is negative. Okay. Now for CEC, right, the separation is really just based on the distribution of equilibrium, just like in chromatography, and we can utilize a coated capillary or a packed capillary. So the materials may actually enhance the EOF because of the charges on the surface. Oops. So it is still not widely used, right? Because the manufacture of this packed capillary, is very much difficult, and we need to ensure that it's a very uniform packing without any void, right, any cavity. So therefore, it's very hard to maintain this quality assurance, and therefore it's not widely used from now. Now for the CEC, just to add on a bit more, right? It is, if you can do the capillary, there's an enhanced VEO, because each silica particle bears its own electrical double layer. Remember, it's O minus, and then you have the charges right under the layer. Similar to the silica capillary, so there's a bit of additional mobile ions, right? Cations, which will be repelled by very high voltage. So there is also additional form of selectivity because of this interaction with the stationary phase. Now, if your X, right, your retained weakly, right, by the stationary phase, it will migrate faster. For Y, right, if it's retained strongly by the stationary phase, it will migrate slower. Makes sense, right? Okay. The next part of the CEC is how we use this schematic diagram to see. Now, for liquid chromatography, just using a pressure drive. You see, remember, it is not a uniform flow, right? Because when you're closer to the wall here, there's some kind of drag force. So this is a velocity profile here. In the middle, it's faster. We call it parabolic profile. Broad peaks might overlap, not accurate. Here in the CEC part, you're having a more uniform flow, right? Because we're using electrical current, so you have a plug-like, sharp peak, so minimizing the overlapping of signals. So here we talk about CIEF, right? The capillary isoelectric focusing is to separate amphoteric species, having both positive and negative charges, right? Depends on the pH, and it's based on the PI, isoelectric points. Okay, so you know that amino acids will have that. Therefore, we used to separate proteins, and we separate protein samples, and the mixture of the ampholites forms a pH gradient inside the capillary, right? So it gives a different kind of electrophoregram. Now, the anodic end of the capillary is placed in an acidic solution. We call it an analyte, analyte because anode, right? Whereas the cathodic end is placed in the basic solution, so catholyte. See the root word and the prefix. Here, CIEF, let's continue. Under the influence of this positive electric field, the charged proteins will migrate right through the medium until they reside in the region of pH, where they become electrically neutral before they stop migrating. Remember, the two sides, right? They have different charges. So when we migrate the ions through one end, slowly being affected by the pH, right, it become, right, let's say we have positive charge, but as we migrate, it become less positive charge, become neutral, and just get stuck there. So the zones are what we focus on, right, when the steady state is reached. After we focus, the zone may then be detected by scanning the detector across the capillary, okay, because we do not know where they are residing, right? You can't just put a fixed detector there expecting to come, may be stationary there. Now then, or we can migrate, mobilize the analyte hydrodynamically, gravity or pressurized flow, or by I think a salt, right? Salt in the analyte, because of by the principle of electroneutrality, the sodium ions, right, can exchange for the protons, which means that now there's a pH imbalance, right? When you add the Na plus, at first the maybe amino acid is protonated by H plus, you can swap, right? So now the H plus comes out, and then you have a little area with a difference in pH, and that causes the migration of the component. So we call this the chemical mobilization. This is a schematic example of how it looks like. At the start, okay, mixtures are together, randomly mixed. You have red, your orange, your yellow, green sample here, and these are your mixture of ampholites, okay, catholyte, anolyte. Now, after some time, you see that, right, the bands are being separated, so those which have similar PI will be together, right? High pH, right? You have the hydroxide here, and low pH H plus, and afterwards, you see, then the zone stop moving, right? Even though it's 2 times your T prime, because they become neutral and is focused. Okay, so a bit more, you can see now it's a better drawn diagram. We narrow it down. Well, when we add chloride to the cathode, right, remember we have this ion exchange. Chloride replaces the hydroxide. Good. So you have less hydroxide, fewer number of hydroxide in the capillary, and then pH will drop, right? Then the ions will move from right to the right to become neutral. Okay, detector is here, normally to the end. So we call this cathodic mobilization, right? Which means the protein is moving to the cathode. It is a competing ions, like we just described chloride, adding to the focusing agent, call this the catholyte, disrupting this equilibrium because you have exchange, right, due to the focusing. Okay, so therefore we allow it to move. Now this part is the opposite. Anodic mobilization works in the same way but in the opposite fashion, right? Because the charge is now different. You add sodium plus ion. Na plus replaces H plus, less H plus in the capillary, pH increase, ions move to the left and become neutral. It's just the opposite. Okay, this way. Now when we have this CIEF with EOF, right, capillary isoelectric focusing, with the EOF example, you notice that the EOF is not eliminated. So there's some good point from here, which is it's convenient, because we don't have to, mobilizing it, adding this, right, still can detect. But the downside is that there's a slight dispersion due to the EOF. So which means that the efficiency is a bit compromised, okay? Maybe it's a bit slower. Next, we go into the capillary isotachophoresis, CITP, performed in a discontinuous buffer system, right? Different buffers, two ends of the capillary. Just now it was two different pH. Sample component condenses between the leading electrolyte and terminating electrolyte, okay? Producing a steady state migrating configuration composed of consecutive zones. So again, by zones, okay, by the bands here. And if both ends in the terminating electrolytes are used, we call it CITP. If there's no terminating electrolyte, cause a moving boundary electrophoresis. Some example of the 4 basic modes of electrophoresis. Here, BGE, right and left, anode LE. So you see different kinds of electrophoregram, right? This is more plug-like, this is more narrow peaks. Here is this isoelectric focusing. pH, you see a gradient. Now for CITP, rather than peaks, right? Like just now in the previous slide, you show that it appears like a step because you represent a zone. Remember, now we look at the zone, the whole window, not just a narrow peak. Okay, because the ions in the same zone move in the same velocity due to the charges. And we do not measure the area underneath the peak. To analyze the quantity, we measure the length, right, which is proportional to the amount of the sample present. So in this case, let's do a recap, right? After some time, right, you separate, you see moving in bands or zones, so we measure this length, the Z1, Z2, Z3 representing them, right, and because it comes out in steps, okay, we don't have peak height or area, take note. This is what we have, one more time. On column transient isotachophoretic preconcentration. What happens is we inject the larger plug, right, see 30 kilovolt is one of the highest, concentrate into a small plug, so you see a difference, pre-concentrate. From a big cavity, you compress it to small, so you increase higher concentration. So when we have high concentration, you have a higher sensitivity. Okay, large plug, small plug, separate better. Okay, so you see here, in the beginning, you have this injection step, leading electrolyte, right? Next part is the focusing step, your ITP, where your terminating voltage here is placed in the reservoir, and then the voltage is applied. And the last step is your CZE, separation step. When it's replaced by the leading electrolyte, you see it change, right? Then the band will split and separate. So in summary, just need to know what are some of the properties and intricacies of each of these different modes of electrophoresis. And then I will see you next time. Cheers.